Good morning. Today we'll be talking about 1,3 dipolar cycloaddition reactions. And when we use this word 1,3 dipolar, that means I would have a 3-atom system in which they'll be having opposite charges on first atom and the third atom. For example, let's say I have a system which is X, Y, and Z. X is first atom, Y is second, and let's say Z is the third atom. Then probably I'll have a positive charge on X and a negative charge on the third atom, that is Z, or vice versa, a negative charge on X and a positive charge on Z. This kind of a species which is involved in these kind of reactions is known as 1,3 dipoles. In fact, 1,3 dipole is a very versatile and a good method to stereospecifically produce or synthesize 5-membered heterocyclic compounds by the addition of 1,3 dipolar compounds, as we have told, to a ethylenic double bond, which we call in this particular case as dipolarophiles, or it can be a triple bond also. So what we are trying to say is that this is a kind of a cycloaddition reaction in which two components are involved. The first component here is a 1,3 dipole, an ionic species having opposite charges as first atom and third atom, and the second reactant in the cycloaddition reaction would be a dipolarophile. If you remember, in Diels-Alder, in cycloaddition or Diels-Alder, we used to call it as a diene and a dienophile. In this particular case, we have a dipole, and the second component which will be attracted to a dipole will be called as a dipolarophile. Therefore, two components are involved, as I've told you. The two components are a 1,3 dipole. 1,3 dipole will have positive charge on first atom and the negative on third, or vice versa. Now 1,3 dipole is such species which will be contributing 4 pi electrons. For example, if I take a simple example of allyl carbonyl, you can see this is a 3-atom species having a pi bond which is contributing 2 electrons, having a lone pair which is contributing 2 electrons. So total electrons contributed by this 3-atom species is 4, and since it is 4, we can call it as a 4 pi component. For example, as in the case of allyl carbonyls, this system which will have opposite charges here, even though the opposite charges are not depicted, those systems which will have opposite charges on first atom and third atom is a 3-atom system which contributes 4 pi electrons in the cycloaddition reactions, would be called as 1,3 dipoles. And the second component which would be involved in these reactions would be either a double bond or a triple bond. Of course, if it is a double or a triple bond, it will be contributing 2 pi electrons to the system. So 1,3 dipole is contributing 4 pi electrons. Second component, which is a double bond or triple bond, is contributing 2 pi electrons, and we call this particular second reactant of this 1,3 dipolar cycloaddition reaction as dipolarophile. So two reactants again. 1,3 dipole contributing 4 pi electrons, has 3 atoms. A double bond or a triple bond called dipolarophile contributing 2 pi electrons, and therefore this reaction is similar or analogous to a 4 plus 2 pi cycloaddition reaction or a Diels-Alder cycloaddition reaction in which two components are involved. First component, as I've told you again, contributing 4 pi electrons, and the second component is contributing 2 pi electrons. Let's talk about various examples in this regard. Let's talk about the examples here. Let's say first component is a 1,3 dipole. Now, as I've depicted here, this molecule, which is what this would be a diazomethane compound in which I have 2 nitrogen atoms, a positive charge on the central nitrogen atom, a lone pair on this carbon atom, therefore a negative charge. Actually, I cannot call this species as a 1,3 dipole. Honestly speaking, I could have written 2 formulas for this. Later on in this lecture, you understand that we can write 2 formulas for a 1,3 dipole. If I write it like this here, for example, it is Cr2 with a negative charge because of the lone pair, and N triple bond N like this, a positive charge here, a lone pair here. I could probably write another resonating structure for this in which this positive charge could be quenched by the movement of this nitrogen electron, and then I would have Cr2, a negative charge on this atom. Nitrogen's positive charge is quenched and has gone as a lone pair. This nitrogen now will become positive charge. Now if we find this species, I can write 2 resonating structures. This species is what? A negative charge on first atom and a positive charge on the third atom. Therefore, I can call this species as 1,3 dipole. So even though I'm writing a positive charge on the first atom and negative on the third, or vice versa, I can write this formula for a 1,3 dipole also, or I can write this formula for a 1,3 dipole in which the charges are on first and second carbon atom. So both are similar things because these are resonating structures. Therefore, I'll talk about this thing that normally for a 1,3 dipole we write this formula which we call as an octet formula. But anyways, as of now, let's say how this 1,3 dipole adds on to the ethylenic double bond or a triple bond. Well, it is easy. The reaction, as in all cycloaddition reactions, is a concerted reaction which proceeds to a cyclic transition state. We normally believe that the reaction is initiated by the movement of this lone pair and towards the formation of a bond between this carbon and this carbon atom. This pi bond breaks, starts forming a bond between this carbon atom and this nitrogen atom. This bond breaks and quenches the positive charge on nitrogen, as the result of which we'll end up in the formation of this 5-member ring, of course through the formation of this cyclic transition state, in which, as you can see, the bond between this carbon, this and this carbon is getting formed. The bond between this carbon was already there. The bond between this nitrogen and this nitrogen was double bond was there. This bond is getting broken. This bond is getting formed. This is the state of affairs as far as the transition state is concerned. This bond is getting broken. So reaction is proceeding through a cyclic transition state as in all cycloaddition reactions, and ultimately you'll end up in the formation of a 5-membered compound. And if other than carbon atoms are present, we call these as heteroatoms. So we end up in the formation of a 5-membered ring which has having heteroatoms. Therefore it's a stereospecific production or a stereospecific synthesis of a 5-membered heterocyclic compound using 1,3 dipolar cycloaddition reactions. Of course, there can be one more step here. This proton can be lost and it can impulse nitrogen atom, and the result is the formation of a more stable pyrrolazine ring. We can talk about another example in which we are taking azide moieties. Azide are N3 species. And if you look at this azide again, we have a nitrogen here which is negatively charged. We have a nitrogen here which is positively charged. Again, this is a isomeric form of 1,3 dipole. This can add to an acetylenic double bond to a triple bond. Again, the formation would be similar. There will be a bond formation between nitrogen and carbon. This bond will break and bond formation between this nitrogen and nitrogen. This bond will break and ultimately a lone pair will be going to nitrogen atom. The result is the formation of this kind of a 5-membered heterocyclic species in which 3 hydrogen atoms are attached. So we call this as triazole molecule. Therefore, as we can see that using 1,3 dipolar cycloaddition reactions, we are using two components. One is a 1,3 dipole. Of course, we can use the octet formula for 1,3 dipole as I've told you. The second component is either a double or a triple bond called dipolarophile. So a dipole and a dipolarophile, they add on to one another. Dipole is contributing 4 pi electrons, as we can see, contributing 4 pi electrons. Dipolarophile is contributing 2 pi electrons. Ultimately, these two add on to one another to form a 5-membered system. Of course, the reaction is concerted, therefore it has to be stereospecific in nature, as all pericyclic reactions are. The best point about the 1,3 dipolar cycloaddition reactions is that like all cycloaddition reactions, this reaction is fast, and because this reaction is very fast, we normally end up in the formation of the product, which in the case of 1,3 dipolar cycloaddition reactions are normally heterocyclic 5-membered rings with great ease. Let's take another example. These are the two examples which will follow are drawn or shown in the so as to show a stereospecificity which is observed in this reaction. Let's take again a 1,3 dipolarophile. You might have noticed that in all previous examples that we have taken, 1,3 dipolar compounds which we have taken as the first reactant of this 1,3 dipole cycloaddition reaction are normally those compounds in which at least some heteroatoms are present. And this is the case in all 1,3 dipolar cycloaddition reactions, that 1,3 dipoles are normally not just simple carbon atom systems, they are those systems in which at least a heteroatom or more than one heteroatom is present. Therefore, that's why it produces a 5-membered ring which has at least one heteroatom. That's why it is a stereo-specific synthesis of 5-membered heterocyclic compounds, as we have talked about in the discussion part of this 1,3 dipolar cycloaddition reactions. Okay, let's take an example in which I have taken 1,3 dipole. Again, I've represented the octet formula here. I've added on to a compound, to an ethylenic double bond, to a dipole aerophile system, in which two carboxymethyls are on the same side. That means this double bond has a E geometry. Both methyls are on the same side. Now, since this reaction is stereospecific, since this reaction is concerted at no point of time during the formation of the product from the reactants, this double bond of the carbon-carbon bond assumes a single bond character, and therefore the substituents here, methyl, two methyls or two carboxymethyls, do not have a chance to rotate and change its geometry. Therefore, whatever is the geometry of the reactants, whatever is the geometry of the substituents in the reactants, the same will be carried on onto products. Hence, if both methyls are on the same side, both carboxymethyls are on the same side, in the product also, both methyls will be on the same side, both carboxymethyls will be on the same side. Yes, the difference can be, you can write two products for this, two enantiomeric products for this, one in which both methyls are above the plane, and the second product will be in which both methyls are below the plane. Hence, the addition is a stereospecific addition, and the geometry of the substituents in the reactant, as I've told you, is carried on onto products. Let's take another example, taking a similar dipole. I've taken this dipole here, 1,3 dipole here. I'll take the similar dipole. Now I've taken an example in which I have a dipole aerophile in which both substituents are having a E or a trans geometry with respect to one another. Now again, during the course of this reaction, this double bond does not assume a single bond character. Hence, whatever is the geometry of the substituents on the reactants, the same will be carried on onto product. Therefore, I'll have a product in which the carboxymethyl is, this carboxymethyl can be above the plane, then this will be below the plane, or vice versa. This can be below the plane or this can be above the plane. So I can write two stereoisomeric products for this, two enantiomeric products for this. One in which carboxymethyl is below on first this carbon atom, and here it is above the plane, and second in which carboxymethyl is above on this carbon atom and below on this carbon atom. Again, but one point to remember is whatever is the geometry trans of the reactants, the same will be carried on onto products. That's the important thing of all pericyclic reactions. The reactions are stereospecific in nature. Therefore, I can generalize a 1,3 dipolar cycloaddition reaction as a reaction in which two components are involved. One first component is called a 1,3 dipole, and 1,3 dipole normally contributes 4 pi electrons in the reaction. Therefore, this is a 4 pi component. The second component is normally a double bond or a triple bonded species. We call, because it is attracted to a dipole, we call this system as a dipole aerophile. So 1,3 dipole and a dipole aerophile which is contributing 2 pi electrons. The result is a stereospecific formation of a 5-membered heterocyclic compounds starting from the two reactants. This kind of reaction is known as 1,3 dipolar cycloaddition reactions. Okay, we'll talk about what are the various kinds of 1,3 dipoles that are available or that we normally encounter in the case of 1,3 dipole cycloaddition reactions. We'll talk about the categories of 1,3 dipole. The first category is 1,3 dipole in which there is a double bond in the between the atoms of a 1,3 dipole and a lone pair on the central atom. What do we mean? I have to have two things in first category of 1,3 dipoles. That is, I need to have a double bond and I need to have a lone pair on the central atom. For example, let's say if I have diazoalkane. Diazoalkane would be nitrogen-nitrogen bond and a carbon atom. This carbon atom is having a lone pair, let's say, and you can count that in this particular case carbon is having 1, 2, 3 and 2, 5 electrons. Therefore, it has a negative charge. This nitrogen's 5 electrons, valency is full, 1, 2, 3 and 2, 5, no charge. If you look at this nitrogen atom, it has 1, 2 and 2, 4. It will not have a lone pair here, sorry. So you should not write it here. This does not have a lone pair. So nitrogen has 1, 2, 4, total of 4 electrons. That's why a positive charge. So we can find a system in which a first category of 1,3 dipoles in which I have opposite charges on first and third atom. So it is 1,3 dipole. We have a double bond between the atoms, 1, that is what is required. And secondly, we should have a lone pair on the central atom, for example in diazoalkanes. Similarly, as in the case of azides, this nitrogen is bonded to some other, let's say carbon atom or something. If you find here nitrogen has 2 lone pairs, 2 bonds, 6 electrons, that's why a negative charge. This nitrogen has a lone pair, this nitrogen has a double bond as a positive charge. So this is again a category of the first category of 1,3 dipoles in which I have a double bond and a lone pair on the central atom. Similarly, nitryl halides. Nitrile halides are C double bond and C lone pair species. Negative charge here, positive charge here, a double bond and a lone pair on the central nitrogen atom. So first category of dipoles are those 1,3 dipolar species in which I have a double bond and a lone pair on the central atom. The second category of dipolar cycloadditions would be, or dipoles would be, a lone pair on the central atom without the presence of a double bond. I do not have a double bond, I just have the lone pair on the central atom. The example is ozone. Ozone, you know, is an O3 species. You have one oxygen atom which has 3 lone pair of electrons, making the total electron count of oxygen as 7. That's why a negative charge. This oxygen has 2 lone pairs, so 6 electrons. This oxygen atom has 2 lone pairs, one from this coming bond, one coming from this bond, so total of 5 electrons. That's why a positive charge. You can see in this ozone molecule, I have opposite charges on first and third atom. First atom, let's say, has positive charge. Third atom, let's say, has negative charge. There is a lone pair on the central atom, one or more than one, and there is no double bond in this species. So this falls under the second category of 1,3 dipoles. That is, that there should be opposite charges on first and third atom. There should not be a double bond, and there should be a lone pair on the central atom. And the various examples. The second example is azomethane halides. Azomethane halides would be this kind of species. Carbon has being a lone pair, a negative charge. Carbon does not have a lone pair on the first carbon atom, a positive charge. Opposite charges on first and third carbon atom. Lone pair on the central atom. No double bond in this species. Second category. And finally, the third category. Third category of 1,3 dipoles are which have a double bond but does not have a lone pair on the central atom. If this is the category of our let's say systems, then we call this particular kind of dipoles as 1,3 dipoles with a double bond only and no lone pairs. For example, vinyl methylenes. Now if you look at this vinyl methylene, again this carbon has a lone pair, that's why a negative charge. This terminal carbon has a positive charge, it has a double bond. The central carbon doesn't have a lone pair. So all this system has is opposite charges on first and third carbon atom, a double bond, no lone pair on the central atom. Therefore this is the third category of 1,3 dipole. So we have discussed 3 categories of 1,3 dipole. 1,3 dipole which has a double bond and a lone pair. Second, 1,3 dipole which has a lone pair and no double bond. Third, 1,3 dipole in which there is a double bond and no lone pair is present. Right. As I've told you before also, 1,3 dipoles can exist. If you find it here, a 1,3 dipole can exist in 2 particular isomeric structures. We call these isomeric structures as sextet formula and the octet formula. Now what is the sextet and the octet formula? Sextet formula normally represents the proper 1,3 dipole. If I have to write a 1,3 dipole, let's say I have X, Y, Z species. Z, let's say, is negatively charged. X, let's say, is positively charged. And you have a lone pair on this Y atom. Now once you move this lone pair here so as to quench X's positive charge, the lone pair will come on Y. Now normally speaking, with the sextet formula, in this particular molecule, we'll have any atom whose octet is not complete. For example, as in this case, let's me put it as an X. X atom, if you count, has 2, 4, 6 electrons. Its total octet is not complete. That's why it carries a positive charge. Y has 2, 4, 6 and 8 electrons total. Octet is complete. Z has 2, 4, 6, 8 electrons. Its octet is complete. X is an atom in this particular 1,3 dipole which does not have its octet complete. Therefore, we call this formula as sextet formula. If you write this resonating structure and this Y lone pair moves on this side, then we'll have this kind of a structure. X's positive charge is now quenched. Y now has positive charge. Look at X. How many electrons, total electrons it has around itself? 2, 4, 6, 8. 8 electrons complete. Y 2, 4, 6, 8. 8 complete. Z 2, 4, 6, 8. 8 complete. Z. Therefore, in the octet formula, all atoms have their octet complete. In the sextet formula, one atom has one atom is there which has 6 electrons around itself. Therefore, between the 2 isomeric structures possible, the octet formula is the one which is comparatively more stable and is normally drawn for a 1,3 dipole cycloaddition reaction. And therefore, this is the formula of choice which we normally use while using a 1,3 dipolar cycloaddition reaction. Let's talk about the sextet and octet formulas in the categories of dipoles which we have already discussed. We'll discuss probably in the first category. Let's talk about diazoylcane, for example. Diazoylcane was this species in which this carbon had a lone pair. Nitrogen here had a positive charge because it has only one lone pair. Nitrogen had a lone pair here. You remember the first category of 1,3 dipoles was a dipole at first and third atom, a double bond, and a lone pair. All you need to do from converting this from the sextet to the octet formula. First of all, why this is a sextet formula? If you look at this carbon atom has 2, 4, 6, 8 electrons complete, so octet rule is completed. This nitrogen 2, 4, 6, 8 electrons complete, but if this terminal nitrogen is there, it has 2, 4, 6 electrons, therefore octet is not complete. If you want to complete the sextet, or if you want to convert the sextet into the octet formula, all you need to do is you need to move this lone pair in this direction to quench the nitrogen's positive charge. This becomes triple bonded. This nitrogen now has 2, 4, 6, 8 electrons. This nitrogen has 2, 4, 6, 8 electrons. Carbon has 2, 4, 6, 8 electrons. So all atoms in the octet formula has its octet complete. Therefore, the better way of representing a diazoalkane in a 1,3 dipolar cycloaddition reaction is through the octet formula. Similarly, an azide molecule, nitrogen's octet is not complete. All you need to do is to move this resonating to convert it into the isomeric form. You need to move this nitrogen's lone pair in this direction. You now create a octet formula. And if you find that the difference in the octet and in the sextet and the octet formula is that in the sextet formula you normally have opposite charges on first and third atom, whereas in the case of octet formula you find that opposite charges are on the first and second carbon atom. Similarly, nitrile halides. As you can see, carbon has a positive charge here, this carbon has a negative charge here, this lone pair moves in this direction, the charges come on first and second carbon atom. Similarly, your diazoalkyne kind of species, again diazomethane kind of a species, if you move this charge here, you'd end up in the formation of an octet formula. And you remember the second category of 1,3 dipoles were one in which we had a lone pair on the central carbon atom and no charges and no double bonds on the in this molecule. So XYZ has a lone pair on the central carbon atom, opposite charges on first and third carbon atom. Again, if you find it this one, this molecule is one, X should have two lone pairs. This molecule is one in which Z has its octet complete 2, 4, 6, 8. Y has its octet complete, let's say 2, 4, 6, 8, but X will not have its octet complete. Therefore, this is the sextet formula. You convert it into the octet formula, all the three atoms will have its octet complete. For example, let's say the example of an ozone molecule. Again, if you want to convert the sextet into octet, you can see here oxygen has 2, 4, 6, 8 electrons. Oxygen has 2, 4, 6, 8 electrons. Here, the first oxygen atom has 2, 4, 6 electrons. Therefore, its octet is not complete. If you want to convert the sextet formula into the octet formula, as I've told you, move this lone pair in this direction. You'll have oxygen's positive charge quenched. The positive charge comes on the central atom. The charges are on first and second atom. Opposite charges on first and second atom. This is the octet formula, the better formula to be represented in 1,3 dipolar cycloaddition reactions. Similarly, this example, therefore, I can say octet formula because it has all the atoms which have its octet complete is more stable, and therefore 1,3 dipolar cycloaddition reactions are represented by dipoles in the octet formula only. Therefore, I can say while using the 1,3 dipolar or while representing the 1,3 dipolars, I can use this reaction in such a way that either I have a double bond between X and Y, it can be triple bond also. As I've represented in the octet formula, the opposite charges were on the first and second atom. Therefore, I've represented this 1,3 dipole in the octet formula. And this is of course the dipolarophile, as I've told you. The two are adding on to one another. The result is the formation of a 5-membered heterocyclic compound. Now, this is something regarding 1,3 dipoles. Now we try to work out that under what reaction conditions a 1,3 dipolar cycloaddition reaction is feasible. And as you know, we have talked about 3 different approaches to work out the reaction condition: the OCD approach, the FMO approach, and the PMO approach. We'll be starting with the OCD approach. We have to work out that what is the nature of the reactant, and as you remember, in the case of OCD approach, which was based on the Woodward-Hoffman law of conservation of orbital symmetry, which said that while transforming from reactant to product, the reactant molecular orbitals and the product molecular orbitals symmetry should remain conserved. Therefore, I have a 1,3 dipole which I'm representing in the octet formula. 1,3 dipole, as I've told you, is contributing 4 pi electrons. The 2 pi electrons, or the 2 electrons, are coming from this double bond, and 2 electrons are coming from this lone pair. So therefore it is a system in which there are 4 pi electrons which are localized or delocalized over 3 atoms. Hence it is a 3 atom 4 electron system, and hence we should be drawing 3 molecular orbitals corresponding to this particular system. Second component is a dipole aerofoil. Now dipole aerofoil has a 2 pi is contributing 2 pi electrons. It has only one double bond, therefore it is contributing only 2 pi electrons. The result is the formation of the 5-membered compound. And what are the new bonds which are formed here? One sigma bond is this, which is new formed, one sigma bond is this, which is newly formed, and one lone pair is formed here in this particular cycloaddition reaction. Therefore, if I repeat again, I have a dipole, let's say XYZ, a double bond is there, Y has positive charge, let's say Z has negative charge. These are contributing 4 electrons, 2 electrons coming from the double bond, 2 electrons are coming from this lone pair. So 4 electrons are delocalized over 3 atoms like an allyl carbonyl, and therefore it is a 4 electron 3 atom system. 3 molecular orbitals are possible. One will be pi bonding, one will be pi anti-bonding, and one will be the non-bonding orbital corresponding to this dipole. And if you talk about the dipole aerofoil, it's a 2 pi electron system, so it is simple. This is a 2 pi electron system, therefore 2 molecular orbitals are possible. Of course 2 pi molecular orbitals are possible, and of course 1 pi will be bonding and 1 pi will be anti-bonding in nature, right? Therefore, on the reactant side, considering the OCD approach in gauging the reaction conditions, I'll be having 5 molecular orbitals, 3 contributed by the dipole, 2 contributed by the dipole aerofoil. I have to place these orbitals on the energy axis efficiently. If you look or talk about the products, in the case of products, as I've told you, there are 2 new bonds which are formed, these 2 sigma bonds, and 1 lone pair is formed. So in all, I have 2 new sigma bonds, and therefore 4 sigma electrons are involved in this reaction. Therefore 4 sigma molecular orbitals are possible, out of which 2 sigma will be bonding and 2 sigma will be anti-bonding. Since there is 1 lone pair and 1 lone pairs do not get involved in any kind of bonding or anti-bonding process, therefore these 2 electrons are localized on 1 atom only, hence only 1 molecular orbital is possible, and that will be non-bonding molecular orbital. Hence on the product side, again I have 5 molecular orbitals, 4 coming from the 2 new sigma bonds and 1 coming from the lone pair of electrons. Now I need to use my logic, or let's say first of all I need to choose a symmetry operation which could probably gauge this reaction properly. Again, as mirror symmetry operation has always been the right choice of symmetry, for the reason that it is able to bisect bonds which are formed and which are broken. And as you can see in the case of your reactant, I had a double bond here which was breaking, I had a lone pair here which was breaking, so this symmetry, mirror symmetry, could probably bisect the bond which is formed. Similarly, since this bond was breaking, this mirror symmetry atom could bisect the bond formed. Similarly, if you look at the product side, this mirror symmetry is bisecting the lone pair here, this mirror symmetry is probably bisecting both these sigma bonds formed. Therefore, a mirror plane bisects the bonds broken and formed, and therefore is the desired or the right symmetry property to be considered for 1,3 dipolar cycloaddition reactions in the OCD approach. And the next step would be, therefore, in considering the OCD approach, would be to draw the orbital correlation diagram. And we know orbital correlation diagrams are drawn in such a way that I write the all reactant molecular orbitals, I write all product molecular orbitals, and then I assign the reactant molecular orbitals and the product molecular orbitals with the symmetry operation and assign them either symmetric or antisymmetric notions. And then I have to check whether the ground state of the reactant and the ground state of the product are correlating, and if they correlate, this reaction is thermally loud. And if they do not correlate, I have to check the correlation up to the first excited state, and if up to first excited state things are correlating, then the reaction is probably photochemically allowed. Now let's draw the molecular orbital for the reactants first. Let's start with the ground state orbital. But before that, our reactant site is what? It is a 1,3 dipole species and a dipole aerofoil. So this is my reactant side, and if you look at the product side, this is my product side, right? And as I've told you, in the reactant, 3 orbitals are being contributed by 1,3 dipole, and 2 orbitals are contributed by the dipole aerofoil. Therefore, if I look at the reactant side, the first orbital, the most stable orbital, should be one in which there should be no node, contributed by 1,3 dipole aerofoil. This is the most stable orbital. There is no node between. Let's say this is psi 1. Next orbital would be contributed by the dipole aerofoil, because the next orbital of dipole aerofoil, which is stable in nature, would be pi 1, which does not have a node between them. So this is the second orbital. The third orbital would be coming from the dipole aerofoil, in which there is one node. And if one node is there, I normally draw the node here, so it is positive. This will become negative. The fourth orbital would be coming from the dipole aerofoil, pi 2 star 1, which has a node, so positive, negative here. And the last orbital would be coming again from the dipole aerofoil, which is psi 3 star, and will have 2 nodes here and here, so positive, a node here, negative, a node here, positive. This is the orbital picture. So if I have to break it down and write, I'd say the 3 orbitals corresponding to the 1,3 dipole aerofoil would be psi 1 having no node, psi 2 having one node, and psi 3 star having 2 nodes. And the 2 electrons coming from the dipole aerofoil would be pi 1 having 0 nodes and pi 2 having 1 node. All I need to do is to place them on the right axis of symmetry, and to do that, what I need to do is I need to understand which will be more stable. That orbital in which there is no node in all 3 atoms would be more stable than that orbital in which there is no node between 2 atoms. Therefore, psi 1 should be more stable than pi 1. Now, considering the stability of pi 1 and psi 2, pi 1 is one in which there is no node, whereas psi 1 has a node. Therefore, a system with one node should be comparatively little bit less stable than this system. Hence, I've drawn pi 1 lower in energy as compared to psi 2. Next comes a system in which there is one node. Therefore, this is more stable than a system in which there are 2 nodes. So that is why we have placed them on the energy axis. Right, now we have to sign the symmetry operation. As I've told you, the desired symmetry operation in this case would be the mirror symmetry. Mirror symmetry will pass through this, and once you pass the mirror symmetry, let's look at the orbital here. If you pass this mirror symmetry, positive and positive are coming in front of one another. Therefore, this orbital is symmetric. Pass a mirror symmetry here, positive is coming in front of positive, again symmetric. Pass a mirror plane here, positive and negative are coming in front of one another, therefore it is antisymmetric. Pass a mirror plane here, positive and negative are coming in front of one another, antisymmetric. Pass a mirror plane here, positive and positive are coming in front of one another, therefore it is symmetric. So we have assigned symmetry operations to all the 5 reactant molecular orbitals, and the symmetry operations are S, S, A, and S. Now we need to focus on the product. What is my product? As I've told you, my product is a 5-membered heterocyclic ring in which 2 sigma bonds are formed, 2 new sigma bonds are formed, and a lone pair is formed. So there are 5 molecular orbitals corresponding to this, 4 molecular orbitals are corresponding to the sigma molecular orbitals, and 1 molecular orbital will be corresponding to the lone pair. And here placing these orbitals on energy axis is simple, because there will be 2 sigma bonding, 2 sigma anti-bonding, and hence if 2 sigma are bonding, the 2 sigma bondings will be more stable than the non-bonding. Then comes the non-bonding orbital, and then will come the 2 anti-bonding molecular orbitals. Okay, how do I draw that? First of all, both sigma bonding, the most stable orbital will be 1. This is the sigma bond, this is the sigma bond, in which there is a bonding overlap and there is no node between them. So this is psi 1. Next orbital will be 1 in which there is a bonding overlap, but there is a node between them. Here is the node between these two, like this, a nodal plane like this. Positive in front of negative, positive in front of negative. That's why this is psi 2 having 1 node. The third orbital is, as I've told you, the orbital of the non-bonding electrons. So this is the non-bonding electron. This is having 1, in which obviously in non-bonding electrons there will not be any node. Then comes the 2 anti-bonding sigma orbitals. While drawing the 2 sigma anti-bonding orbitals, first orbital is 1 in which positive is interacting with negative. This positive is interacting with negative. So I do not have a node here, but I have a node here and I have a node here. So there are 2 nodes, one this, one this. And finally, psi 4 star having 3 nodes. I have a node here, positive, negative, negative, positive, a node here 2, and a node here 3. Therefore, in all I have 3 nodes. So for product side, it is easier to write or place the orbitals on the energy axis. First two orbitals are sigma bonding, then comes the non-bonding, then comes the sigma anti-bonding orbitals. And you know how to draw these orbitals. We have practiced this in the OCD approach previously also. Now I need to assign the symmetry property to these orbitals. Now again, the symmetry operation chosen was the mirror plane. This is the mirror plane of symmetry. And if you come here and place the mirror here, positive is interacting with positive, positive is interacting with positive, therefore this is symmetric. Place a mirror here, positive, negative, positive, negative, anti-symmetric. Place a mirror here, this should bisect this lone pair, and therefore equal halves are there, therefore this orbital has to be symmetric. Positive, positive, negative, negative is symmetric, and positive, negative, negative, positive is anti-symmetric. Hence we have drawn the reactant molecular orbitals, we have drawn the product molecular orbitals, and then try to correlate, and then we have assigned symmetry operation corresponding to the mirror symmetry property to all these molecular orbitals. Of course, in the OCD approach, the next point would remain, how do we draw the correlation or the OCD diagram. Now OCD diagram drawing is simple. One is reactant, another one is product. The reactant side was psi1 most stable, then pi1, then psi2, then pi2 star, and then psi3 star. And this was the symmetry properties, SSAAS on the reactant side. Product side had sigma 1 bonding, sigma 2 bonding, non-bonding, sigma 3 star, and sigma 4 star. The symmetry properties, symmetry assignments was SASAS. The ground state is up to psi2. Psi2 star is the first excited state orbital. This is the ground state. This is the excited state, right? Now if you look at the correlation, S correlates with S, S correlates with S, up to this is the ground state. A correlates with A, therefore I can say there'll be 6 electrons, 2 will be coming here, 2 will be coming here, 2 will be coming here. Similarly 6 electrons in the product, 2 will be coming here, 2 will be coming here, and 2 will be coming in the non-bonding orbital. So I can say pi1, psi1 2, pi1 2, and psi2 2 correlates with phi1 2, phi2 2, and non-bonding 2 electrons. And since the ground state reactant orbitals are correlating with the ground state product orbitals, therefore I can say with the help of OCD approach that these 1,3 dipolar cycloaddition reactions are thermally allowed in nature. And of course, since these reactions are thermally allowed, photochemically they will be forbidden. You can check this also. If you talk about the photochemical aspect, 1 electron from the psi2 in the reactant side will go to pi2 star, 1 electron from the non-bonding would go to, again a hypothetical situation, 1 electron from the non-bonding will go to the phi3 star. Now if you start correlating up to this level, you'd find that S matches with S, S matches with S, A with A, but A does not match with S. So there is no correlation between the reactant molecular orbitals and product molecular orbitals up to first excited state. Hence this reaction is photochemically forbidden in nature. Therefore, using the OCD approach, we can tell you, or we can explain that like Diels-Alder cycloaddition reactions, 1,3 dipolar cycloaddition reactions are also thermally allowed. Of course, we are not mentioning anything, and the state of affairs would again remain the same, that since nothing is mentioned, the stereochemical mode operative is supra in nature. Okay, let's try to explain the same result using the FMO approach. You remember that the FMO approach was based on the concept that why consider the interactions between all orbitals? Why not consider interactions between those orbitals which are actually involved in reaction? And it is normally the valence orbitals which are involved in the reactions. Therefore, it is the HOMO-LUMO interaction in the case of cycloadditions which are to be considered using the FMO approach. Therefore, I need to work out the HOMO and LUMO of 1,3 dipoles, and I need to work out the HOMO and LUMO of the dipole aerofoil. Now, as I've told you, 1,3 dipole was a 4pi electron system. Therefore, it is a 3-atom 4pi electron system. Therefore, there are 3 molecular orbitals corresponding to the dipole. 3 molecular orbitals are psi1, psi2, psi3. The first 2 electrons will go to psi1. Since 4 electrons are to be accommodated, the next 2 electrons will go to psi2. Hence, the HOMO in the case of your 1,3 dipole would be psi2 and LUMO would be psi3 star. And this we are talking under thermal conditions, of course. And the second component was your dipole aerofoil, which was a 2pi electrons, and therefore pi1 was HOMO and pi2 star was LUMO. Of course, we are talking this under thermal conditions. So using FMO approach, what we need to do is we need to study the interactions of these reactions with the HOMO-LUMO interaction. Okay, let's take both the alternatives. Let's talk about first of all the HOMO of the dipole and the LUMO of the dipole aerofoil. Now HOMO of dipole is psi2 with one node. LUMO of dipole aerofoil will be pi2 star with one node. So if there is one node in 1,3 dipole, one node will come here on the atom, odd node on odd system is here. So if this is positive, this will be negative, this is negative, this will be positive. And if you talk about LUMO, which is pi2 star, this is one node, there will be one node here, a negative and a positive here. And as you can see, this negative has a negative anti-bonding interaction here, positive interacts with positive in a bonding interaction. So suprafacial reaction on both components. The stereochemical mode, as I've told, is supra-supra. The reaction conditions would be thermally loud. Alternatively, if I've taken HOMO of dipole and LUMO of dipole aerofoil, you can take LUMO of the dipole and HOMO of the dipole aerofoil. If I talk about LUMO of the dipole, it is psi3 star, and psi3 star has two nodes, as we know. And if you talk about two nodes, the two nodes will come here and here. So if it is positive here, with the node will be negative, with the node will be positive. Of course, this will be negative, positive, negative. And if we talk about HOMO, HOMO would be one in which there will be no node. If this is negative, I draw this negative, no node, this will be negative. Look at the supra interaction. Negative interacting with negative is bonding interaction. Negative interaction with negative is bonding interaction. Of course, at both the both the lobes there are bonding interactions, hence this reaction is thermally loud. Therefore, using the FMO approach also, we can say that 1,3 dipolar cycloaddition reactions are thermally loud. Of course, if this reaction is thermally loud, following the rules of pericyclic reaction, this reaction has to be photochemically forbidden. And when I say this reaction, I talk about the supra-supra stereochemical mode. So I'm not drawing that photochemical component in the FMO approach. Of course, you can. And using the third approach, I need to work out at the same reaction conditions. The third approach was the PMO approach. The PMO approach was based on the Woodward-Hoffman law of conservation of orbital symmetry, wherein we draw the most stable transition state following from the reactant to the product. And what is that? I have two components again here. First component is 1,3 dipole, which is contributing 4 pi electrons. The second component is the dipole aerofoil, which is contributing 2 pi electrons. So this total transition state will be having 4 pi plus 2 pi, that is 6 pi electrons in the system. Since I have to draw the most stable orbital, the best possible bonding interaction has to be shown. I'm talking about the supra-supra stereochemical mode. So this is the interaction and this is the orbital picture. 4 electrons coming from this, 2 electrons coming from this. Therefore, this is a 6 electron system. The mode of stereochemical mode as depicted is supra-supra. 6 pi electron systems according to Huckel rule with 0 node. Since the number of nodes is 0, I should write here nodes are 0. 6 pi electron system with 0 node are, according to Huckel's rule, aromatic, and all aromatic transition states according to PMO approach proceed under thermal conditions. Hence, as seen in previous two reaction methodology gauging techniques, that is OCD and FMO approach, PMO approach leads to the same conclusion that these reactions, 1,3 dipolar reactions, are thermally loud. So if I sum it up, 1,3 dipolar reactions are a kind of cycloaddition reactions which involve two components. The first component is a 1,3 dipole, which is a 4 pi electron system having 4 electrons contributing 4 electrons but on 3 atoms. And the second component is a dipole aerofoil, which is normally a double or a triple bonded species contributing 2 pi electrons. The result is a stereospecific formation of a 5-membered system. Normally these 5-membered systems are heterocyclic because 1,3 dipoles are normally or generally containing a heteroatom in between them. One or more than one heteroatom is normally present. Therefore, in order to generate a 5-membered heterocyclic technique, 1,3 dipolar cycloaddition reactions are very easy and common techniques to prepare these compounds in a stereospecific manner. And 1,3 dipolar cycloaddition reactions can be categorized in terms of the dipoles as 3 different categories. There are 3 different dipoles. 1,3 dipoles can have a 1,3 dipole in which there is a double bond and a lone pair on the central atom is one category. The B categories if there is only a double bond and no lone pair, and the C categories if there is only a lone pair and no double bond. And then we have tried to work out the more stable octet formula out of the two from the sextet and the octet formula. It is the octet formula which is more stable and normally represented in 1,3 dipolar cycloaddition reactions. And finally, we have tried to work out the different approaches. We've tried to work out the reaction conditions using different approaches, namely the OCD, FM and PM approach, and have worked out that 1,3 dipolar cycloaddition reactions under, of course, supra-supra, the default stereochemical mode would be the thermally loud reactions. So this is it for the day. In the next class we'll be talking, or in the next lecture we'll be talking about the rates of cycloaddition reactions. Thank you so much.